Right, hi there. Welcome to the next set of topics. I'm Dominique Clogg, and I'm going to talk you through the calculus and the trig topics. First, I want to cover the proving by mathematical induction. Now, I think it's quite important that you understand that you're not proving a particular formula, you are verifying that it is true. Okay, so I'll explain that as we kind of go through some examples. But the other thing to bear in mind is that this is often question one, and it tends to be considered a theory question. And so it's quite important that you set it out correctly. Many students actually lose marks not because they don't know how to do it, but because they're actually not setting it out correctly. Okay, so let's have a look at the steps for proving by induction. Okay, so the very first step is that we always prove true for n equals 1. In other words, we're going to prove that the formula holds true for the first term. Okay, now obviously if it doesn't hold true for the first term, then we're not going to even proceed from there. Okay, so what do we do with this sort of thing? We just stick a 1 in for all the n's that we see and we show that it works. Okay, as we do the example, you'll kind of see what I'm talking about. Our next step, we assume true for n equals k, so that it's not just true for the variable n, but it's also true for the variable k. So in other words, it is true for a fixed number of terms. And that's what we assume true. So what do? We stick a k in for all the n's and we say it's true. Okay, nice and easy so far. Then the next part is that we now prove true for n equals k plus 1. So again, what we're saying is that if our formula or our series holds true for a certain number of values, does it, on a certain number of terms, does it hold true for the next term and the term after that and the term after that? And that's why proving true for n equals k plus 1 is so important in verifying why this formula is true. And then obviously our step 4 is that we conclude true for all values. Okay, so let's go through some examples. Okay, so the first thing we're going to do is we're going to prove by mathematical induction. Okay, so if you look here, I've already highlighted this, but I sincerely hope that you recognize this formula and that it is the sum of a geometric series. Okay, so we want to prove by mathematical induction that the sum of a geometric series is equal to a 1 minus r to the k. You know the formula well. Okay, so let's start with this, and we say, right, I always start by actually expanding the series. So in other words, if it's given in sigma notation, get the series expanded, take a good look at what it looks like. So when I put k equals 1 into k's place, I'm going to get ar to the naught, so I'm going to get a plus ar squared, all the way to my final term of putting n into k's place. Okay, and I have my formula. So how do we go? We say, right, our step 1 is that we prove true for n equals 1. In other words, we want to prove true that the first term is in fact a. So what do? We go to the left-hand side and we find the term that has an n in, because what are we going to do? We're going to stick 1 into any n's place. So if I look here, I'm looking at this term in particular on the left-hand side because that is the general term for each of those. And what am I going to do? I'm going to put 1 into n's place, and voila, I get a. All right, then I go and I do the same thing for the right-hand side, and same thing. I just put 1 into n's place, and I can see that it holds true for the right-hand side as well, and so therefore true for n equals 1. Right, what was our step 2? Assume true for n equals k. What do? We stick now a k in n's place. Okay, and so in our formula, wherever we see an n, we replace it with a k. Okay, nice and easy. And believe it or not, that's about 3 marks. Okay, that whole thing. Okay, so now let's have a look at, so there's our second term, our step 2. Now let's have a look at step 3. So we want to now prove true for n equals k plus 1. And this is the important part, okay? And this is the step where actually quite a lot of marks is allocated towards. So what we want to do, as I said before, is we want to now see if the formula is not just true for the first 7 terms or the first 9 terms or 10 terms. We want to know, is it true for the k plus 1th term? Because if it's true for the k plus 1th term, which is the term after wherever it ends. And if we keep going like that, then obviously it's going to hold true for all values of n. Okay, what I like to do with this step 3 is to first put where I'm going. So in other words, what I'm required to prove. So I'm going to put the same series here, a plus ar squared, all the way to plus ar to the k minus 1. And then what am I going to do? I'm going to add on one more term, which is the k plus 1 term, and I want to see if my formula holds true. Okay, so what do? I just replace k plus 1 with k. But remember to first write that whole formula down first, and then put k plus 1 into k's place. Okay, all right, then I now want to prove. So basically, I'm taking this left-hand side and I want to make it look like the right-hand side. Okay, so whenever you are proving, and you must remember this, it is so important that you have to use something in step 2 to prove step 3. Okay, so if I look at this, I can see that that part of my required to prove is exactly the same as what my assumption is in step 2. So I'm going to replace this AR plus AR squared all the way to AR to the K minus 1 with what it is equal to. And then I'm going to add on my next term that I added. And I can see my ones are going to cancel. So I'm left with plus AR to the K. Now I need to make it look like the right-hand side. So I can see I want to find an LCD. And this is really grade 9 maths. I multiply through by my LCD, and I can see that when I apply the distributive law, my middle terms minus ARK plus AR to the K is going to cancel. I can then take out a common A, and I'm left with 1 minus R to the K plus 1. Okay, and that is looking very pretty because it is looking exactly like my right-hand side. Therefore, left-hand side equals right-hand side. So what's my step 4? And I'll put it in as my conclusion, which is by the principles of mathematical induction, which you can actually abbreviate to PMI. It is true for all n is an element of natural numbers. Okay, in other words, you are saying that I've been through all the steps and they all hold true. And so therefore I can say that it is indeed true for all n is an element of natural numbers. The next type of proving by induction that they like to ask you is not one with a series, but rather one that requires divisibility. Okay, so if I look at this question, it should actually say prove by mathematical induction that the following algebraic expression is divisible by 4. Okay, so you can see you're still going to follow the exact same steps, but you don't have an equation this side. So you don't have a left-hand side and a right-hand side. But we still start by saying step 1, prove true for n equals 1. What does that mean we do? We replace 1 with n. And we check that when we substitute 1 into n's place, we get an answer which is 28. And therefore, that is divisible by 4 and hence true for n equals 1. So we didn't actually need a left-hand side and a right-hand side. Okay, what's our step 2? Assume true for n equals k. So what do? We replace n with k and basically saying it is true for all variables. Now, again, let's have a look here. Once you go through, you've got to somehow prove or show that it is in fact going to be divisible by 4. So what do? We use a different variable. So I've used k here, so I'm going to use equal to 4p. You could use mt, whatever you want, but p is an element of z, and I make sure that if it's asked, if the question is that show that it's divisible by 4, I have 4p. If it's divisible by 6, I'd have 6p. Okay, because remember divisible by 4 means a multiple of 4. All right, so what's my step 3? I now prove true for n equals k plus 1. So I want to know if I put k plus 1 into k's place, is it still going to continue to be divisible by 4? So remember the first thing I do in step 3 is I put where I want to go. So I want my required to prove to be that I now replace n with k plus 1. Okay, so I have 5 to the k plus 1, 4 times k plus 1 plus 1 plus 3. And remember, I want this algebraic expression to be divisible by 4, which really means that as you must see it, is that at the end, you want to be able to take out a common factor of 4 so that you have 4 times something. Okay, all right, now we've got to prove this. Now, when you're proving anything with exponents, the easiest thing to do is to split any exponent up. So in other words, if I've got 5 to the k plus 1, split it into 5 to the k times 5, and then inside this bracket is simplified 4k plus 5 plus 3. Okay, all right, now remember what I said to you? In order to prove now, because we've got to now get this to have a common factor of 4. Okay, but as I pointed out to you, you've got to make sure that you use something from step 2 to prove step 3. Okay, so let's have a look. From step 2, I can say that 5 to the k times 4k plus 1 is equal to 4p minus 3. So the reason I do that is that I want to make sure that something here, I try and manipulate it to make it look like this so that I can replace it with 4p minus 3. Okay, because remember, you have to use something from step 2. All right, so the first thing I'm going to do is this bracket is bugging me because I definitely need it to be a 4k plus 1. So I'm going to rewrite it without changing the value into 4k plus 1 plus 4. Okay, it's now looking a little bit better. Okay, so now I'm going to apply the distributive law where I almost treat this 4k plus 1 as one term. So I'm going to have 5 times 5 to the k times 4k plus 1 plus 5 to the k times 5 times 4, okay, plus 3. And the reason I want to do that is because I've now made something in my proof look like something from step 2. Okay, so I can now replace the 5 to the k and the 4k plus 1 with 4p minus 3. And so what do I end up with? 5 times 4p minus 3 plus 20 times 5 to the k plus 3. Now, it might look messy and untidy because you've got p's and k's, but we actually don't mind. We don't mind how many different variables there are as long as I can take out a common factor of 4. So when I distribute this, you can see that you actually have got 20, 12, and 20 as your coefficients. So what can I do? I can take out a common 4. Not really interested in whatever's inside this bracket. All I know is that I took out a common 4, which means that my expression is divisible by 4. Hence, I can conclude by saying by the principles of mathematical induction, that would be the correct way to write this, is true for all values, for all n as an element of natural numbers. Okay, and the last example I want to show you is something that's a little bit different. It's not a series, and it is not a proving by divisibility, but it's actually a formula that you know quite well. So it's the derivative of a polynomial with a power of n, which you know that through core maths, we actually just kind of tell you what the formula is by looking at the pattern, and it's nx to the n minus 1. So this formula has been proved. We're now going to prove it by induction to verify that it is in fact true. Okay, so let's start with our step 1. I'm going to go through this quite quickly, but what am I going to do? I'm going to put n equals 1 into the left-hand side and the right-hand side. In other words, wherever I see an n, and I can see that the derivative of x to the 1, now I don't need to use my rules to know that the derivative of x, it's a straight line graph that has a constant gradient. If you think about it as y equals x, the coefficient of x is 1, and so the gradient of the line is 1. Okay. If I look at the right-hand side, which is plugging into my formula, I put 1 into n's place, and 1 times x to the power of 0 is 1. Therefore, true for n equals 1. Right, what's my next step? Assume true for n equals k. I replace everything I see with n with a k. And I then go on to my step 3, and I now want to prove true for n equals k plus 1. So what does that mean? I want to put k plus 1 into n's place, and I want to check if it holds true, if this formula holds true for the k plus 1th term. Okay, so remember what I said, when you've got exponents, the first thing we do is we split them up. Okay, so I'm going to say that the derivative of x to the k plus 1 is equal to the derivative of x to the k times x to the 1. Or I could have done left-hand side and then just shown this part. Okay, now if you look at this, this is the derivative of the product of two algebraic expressions. So what are we going to apply? Our product rule. But when we differentiate, so how does the product rule go? We differentiate the first, leave the second. Plus, leave the first, differentiate the second. But remember that when you are differentiating, you're not differentiating just plugging into the rule. You are differentiating using step 2 or knowing the derivative of x to the 1. Okay, so let's have a look at how we break up. Because remember that when we are actually doing the proof in the step 3, we have to use something from step 2. So we have to use that formula. So when I differentiate x to the k, because remember the product rule means differentiate the first. So when I differentiate x to the k, what am I going to be left with? K x to the k minus 1 using the step 2 rule. Okay, times by the derivative, leave the second term, which gives me x, plus leave the first term, which is x to the k, times the derivative of x to the 1, which we know, because it's got a constant gradient, is equal to 1. Okay, I then split up my exponents so that I can neaten it up. And you can see you've got x to the minus 1 times x there, so they're going to cancel, and so I'm left with it nice looking like that. And what can I then do? I can take out a common x to the k. Remember always to let the right hand side guide you, and if I simplify the right hand side, which I didn't do here, you can see that you're going to have k plus 1 x to the k, because 1 minus 1 is going to cancel. Okay, so watch out for these weirder ones. They still follow the same rule. It just looks different, and so sometimes people get scared because it looks different. But I promise you, just follow the same steps and it all tends to work out. And just remember that in your step 3, you have to use something from step 2 to prove. Okay, all right, I hope this has been helpful. Please make sure that when you go through the revision worksheets that we've given you that have full solutions, that you go and do all the proving by induction, because this is actually, they are nice, easy marks to get, and it gets you on the right track.